Yes, I will talk about a work that joins the questions raised on during Karenin's presentation regarding the coupling of decision model and and an epidemiologic model from a theoretical point of view. So for a quick overview on the context and motivation on this work, I am interested in a livestock disease that spreads dynamically on a trait network. There is a network structure that is directed, weighted, and, well, in particularly scale-free. And I want to count for human decision-making regarding the adoption of voluntary control measures by the farmers, and in particular for endemic unregulated diseases for which control is not compulsory. So, well, regarding existing models that could address this problem, there are many elements present in other works, but there are some elements of the previous context that are not present. So, for example, behavioral epidemiology has dealt with this voluntary adoption, but generally on a non-structured population. So there is the network structure that is not present. Sometimes it's the human decision-making that is not present because decisions are made by a central authority. Well, there are not many works that concern voluntary adoption of measures for livestock diseases and even less for unregulated diseases. So our objective was to elaborate an integrative model that could couple the dynamic of the epidemics on the network and the dynamic behavior, farmers' behavior, and regarding the control measure. So for this, I will detail the two components of the integrative model. So the epidemic model consists on an intra-herd stochastic model, an SIR model, that accounts for demography and for the trait network, so the animal transfers, and it was modeled as a continuous time Markov chain. Well, that was very fast on the epidemic model, and now I'll detail the farmer's decision model. So first, we set a dynamic decision model for each farmer that mainly consists on supposing that each farmer searches to take a decision, so applying or not applying the measure in its herd at each decision time in order to minimize unexpected cost related to the decision, which is well, stochastic, since the epidemic spread is stochastic, and in advance it can know what the best decision would be. So it's a dynamic decision problem under uncertainty, and with this decision problem in mind, we proposed an approach for representing farmers' decision process for making decisions, inspired by Kuga and co-authors, among other works, where decision is evaluated after being applied, and the preferences the farmers have for a decision and another are updated through time. So we have an algorithm that represents different aspects of farmers' decision making, such as learning. The algorithm is stochastic, and I will detail how an imitation feature is done. So I suppose that at each decision time, each farmer chooses a decisions whether to apply or not apply the measure in its herd, and observes a cost related to the previous decision. And in the meantime, he can observe what another herd does, so a neighbor in the trade network, so a herd with which it exchanges animals, and well, can observe not only his action, the neighbor's action, but also the neighbor's observed cost, and well, he updates the probability of applying the measure, where the update lies on using a linear combination of its own cost, observed cost, and the cost observed by the neighbors, and where there are weight parameter, two parameters that weight the importance that the two costs take for the probability update. So we measure at what point farmers are sensitive to the observed costs. So I detailed this model for a vaccine that protects susceptible animals with a certain efficacy during a period that lasts until the next decision time. And for this measure in particular, I defined a cost function that mainly counts, well, for one thing, the vaccination cost, if the vaccine is applied at time t by farmer G, and a cost that consists on the economic impact of new infections in the herd following the decision until the next decision time. And there is also a normalization per animal so that costs are comparable among different herds of different sizes. So this is the schematic representation of the integrative model where I detail well, I represent how the two components, the epidemic demographic and the decision component, are linked through the decision, the control measure, and the observed cost function, and where there is also well, the impact of the neighbor's action and costs. So now I will present simulation results on the basis of this model. So for the simulation setting, we used 500 hertz, and we fixed demographic parameters, and we simulated a network structure that could reproduce the main characteristics of the network of French administrative area, Finistère. And I fixed the 13 parameters of the model to realistic value. Only the parameters regarding the sensitivity of the farmer to his own cost and to the cost of the neighbor were explored. I mean, two values were explored. So here I present the results of the epidemic spread over 3 years, where I explore the proportion of infected herds over time and the proportion of infected animals among infected herds in the two setting of parameters, so of decision parameters. So when farmers are not very sensitive to the cost, and where they are very sensitive, so in yellow and in light blue. And I have two other scenarios for comparison: a scenario where there is no vaccination, and a scenario where at every decision time, so here is every 6 months, all farmers vaccinate. So for start, we can see that the global gain of vaccination concerns mainly inter-herd prevalence, as intra-herd prevalence is already rather low, even if in the scenario where there is no control. And for well, the other remark is that farmer sensitivity to cost, so the two decision-related parameters, determine, for one thing, the proportion vaccinated from the second decision time. So here it is represented by these blue and yellow points. So this, for example, here at the beginning, only 1% of farmers vaccinated, and from the second decision time, it is almost 50%. And when farmers are not very sensitive to cost, this proportion of vaccinating farmers increases, but much more slowly. And of course, this determines how quickly interherd prevalence declines. Okay, so now I will I show you an explanation on the decision patterns over the 3 years, where in these figures I have well, the scenario where farmers are not very sensitive to cost and were very sensitive. And what we observed is each color represents a vaccination pattern, and the width represents the frequency of the pattern. So, for example, here the most frequent vaccination pattern was to never vaccinate. And what we can remark from these two figures is that at each decision time, the group of herds that has changed the previously the immediately previous decision is not always the same. As we can see, there are many vaccination patterns. And now I will show you sensitivity analysis that we performed of the model in order to study how much the variation of the 13 parameters I initially fixed could make variate the outputs of the model. In particularly, we perform a multivariate sensitivity analysis based on principal component analysis and ANOVA. And for the outputs, since the model had different components, we considered well, different kind of outputs. So 5 different epidemic outputs, 1 economic output, 2 decision-related ones, and 1 output that combines the epidemic and the decision component. And well, I will only detail I will only show the results for one of the sensitivity analysis experiment, where that was done on the means of all the outputs I just mentioned, and where the epidemic parameters were fixed, since they showed to be the most influent ones, if not fixed. So under this scenario, the most influential parameters in the main effect were the vaccine efficacy, the duration between the 2 consecutive decisions, and the initial probability of vaccinating, and that is the same for all farmers. Just as a note, the vaccine efficacy and the initial probability of vaccinated had a globally positive impact on limiting disease spread, since they have a positive impact on vaccinating, and the duration between 2 decisions had a negative one. Okay, so as a side note, I just wanted to mention that we are developing an application and an extension of this integrative model to VVD, where we could consider that information network is not the trait network, but another kind of network. So, for example, the geographic network. Yes, so only to conclude, the integrative model based on the two submodels, and the simulation and sensitivity analysis can be found in an article we published this year. So you can read it if you are interested in the details. Thank you.
Thank you, Lena, for a very interesting talk. So, do we have any questions in the audience? So I can. So I don't see. There's nothing.
You have a question from Egil.
Yes, Egil, please.
Hello. Thank you very much, and I really enjoy that you try to combine the decision making and the epidemiological modeling. I was wondering, you mainly showed now the sensitivity analysis for the socioeconomic or the decision making part. I was wondering, I've used kind of a toy model in a publication, and we found that actually the epidemiological parameters were not, so the model was not really sensitive to the epidemiological models parameters. So how is that in your work?
Yes, thank you. Sorry. Yes, I only showed the results when I fixed it, but overall, in my model, I didn't find the same thing as you say, because the epidemiological parameters were the most influent ones over on the means of all the outputs I considered. So that was I thought it was less interesting as a result. So that's why I didn't.
No, I understand, but I was just wondering, because we found that they were not, in our case, they were not so sensitive to it.
Okay.
Okay, thanks. Great work.
Thank you.
Any other questions? So I have a question about you. You ran, when you did that sensitivity analysis, it was quite many scenarios. I think it was over 600 different data points that you ran. So how, I imagine this must have taken a long time to run all these simulations.
Yes, sorry. Yes, I split simulations over different nodes of a simulation cluster, and I tried to optimize my code so that each simulation for a fixed setting of parameters lasts 1 minute, and I did 50 runs by combination. 1 minute for the 3 years that I simulate. So at the end, well, I split it in 25 nodes. So at the end, I think each of the 25 that run in parallel run for 24 hours.
Yeah, that's not so bad. So what is it, this emulsion that you are using for this specific disease spread model we are developing now?
Sorry, I'm not, I didn't.
Is it this emulsion software you're using for this disease spread?
Yes. No, I am, since I wanted to consider well, vaccination and to manipulate the model myself, I recoded in Python the things that I needed from emulsion. But yes, it is completely based on their work.
Is it all available on like GitHub or something? The code?
Oh, sorry. For VVD, I'm working on it, but this work on the generic model and the SIR model is available on GitHub, and the link is in the published article.
Yeah, thank you.